So let's have a look at Leaving Cert 2006, question 7 from the physics paper. This question will be 56 marks. Typically should take you about 20 minutes to carry out this question. This question is all about lenses, refraction, power of the eye, and so on. So it's bringing together a lot of topics that you've already studied. So let's have a look at this question in your notes. So it's question number 7. First thing they're asking you, what's meant by refraction of light? That's just a simple definition. And there's 2 things you've got to get into this answer. The first thing I want to get in is it's a changing of direction of a wave when it enters a region where its speed changes. So they're the 2 things I want to get in, speed changing and changing of direction. So 6 marks for that, probably 3 for each of those. Next part. They're saying a converging lens is used as a magnifying glass. Draw a ray diagram to show how an erect or an upright image is formed by a magnifying glass. So you should know your ray diagrams really, really well. So here's a diagram on the board of my convex or converging lens, and I want to use it as a magnifying glass. Well, where do I put the object? Well, it's important that I put the object inside the focus for that to occur. There's my object, O. Now I'm going to take 2 rays of light. You've got 3 construction rays in total. My first one, as always, is from the tip of the arrow, a ray of light parallel to the principal axis. You know what happens to it. It will be refracted through the focus on the opposite side. We'll then have to take our 3rd ray of light, which is a ray of light from the tip of the arrow through the optical center of the lens. Will pass through undeviated. And you can see what happens to those 2 rays of light on the far side. Those 2 rays of light are diverging. They're never going to come together, but they may come together in someone's mind's eye. So if I put my eye in here, and then I work them back from where they came, as such, and they're going to meet somewhere back here. So my 2 rays of light will meet there. The tip of the arrow will finish here. All other points will finish down to the principal axis. I'm not going to do all the other points. I'll just do the tip of the arrow. But you can see that all the other points will finish down here. I'll put a kind of a broken line, the broken line telling me that it's a virtual image. So my image eye is formed here. So all they're asking me is to draw that ray diagram. So that ray diagram is drawn. There's 12 marks for that. You'll get marks for showing the setup. You'll get marks for your 2 rays of light. You'll get marks for showing where your image is formed. Back to my question. Next part. They're saying a diverging lens. You know what a diverging is also called? It's also called a concave lens. Cannot be used as a magnifying glass. Why can it not be used as a magnifying glass? I suppose the key is in there, isn't it? The word magnifying. Because when you've got a concave lens, you've drawn all these diagrams before, it always produces a diminished image. So that's what you've got to get in. So it can't be magnifying, obviously, if the image is always diminished. So 5 marks for saying that. Next, let's get on to the meat of the problem, the mathematical, the intelligent part of the question, the part that we're really interested in. So it tells me that the converging lens has a focal length of 8 centimeters. That's a real focus, so F will be +8. They're asking me to determine the 2 positions that an object can be placed to produce an image that is 4 times the size of the object. Now, when I say 4 times the size of the object, They're not saying real or virtual, so I've got to take both into account. One will be real, one will be virtual. So I've got f is equal to plus 8 centimeters. Well, there's 15 marks for this. You're probably going to get 6 marks for writing down the formulae. The formulae I'm going to use are 1 over u plus 1 over v equals 1 over f. That's your main lens or mirror formula. And you've also got your magnification formula, m is equal to v over u. Well, you're going to talk the two object positions. One will be a real image and the other will be a virtual image. So let's start off by looking at the real image. Well, if the magnification is 4, in this first case, m will be equal to plus 4. Now you know that m is equal to v over u. So v over u is equal to 4. Slide the u up, so you end up getting v is equal to 4u. Put a box around that. You don't know v and you don't know u, but you do know the relationship between them. Now I'm going to use my other formula. I have f is equal to 8. I don't have u and v, but I do know that v is equal to 4u, so I'm going to replace v by 4u in there. So now I've got 1 over u plus 1 over v, 1 over 4u is equal to 1 over f, 1 over 8. So what I'm going to do is I'm going to multiply right across by something that will get rid of all those fractions. And what will I multiply across by? We'll multiply right across by 8u. So multiply every term by 8u. And that will get rid of all the fractions for me. So u into 8u goes 8 times. 4u into 8u goes 2 times. And 8 into 8u goes u times. So you can see there that I end up getting u is equal to 10 centimeters. That there is outside the focus between f and 2f. You know the situation then you want to do is for the virtual image. Now I've got m is equal to minus 4 because it's virtual. V over u is m, and that's minus 4. Slide the u up. V is equal to minus 4u. Put a box around that. You don't know v and you don't know u, but you do know the relationship between v and u. So now put them into my formula. 1 over u. Replace v by minus 4u. Throw the minus in front of the fraction. So I get minus 1 over 4u. And that's equal to 1 over 8. So once again, I'm going to multiply right across by 8u. Every term by 8u. So I end up getting 8 minus 2 is equal to u. So in this case, u is equal to 6 centimeters, which makes sense. If you're going to get a virtual image, of course, that's got to be less than the focal length. The focal length is 8 centimeters. So 6 centimeters means I'm inside the focal length. Right, moving on. It says the power of an eye when looking at a distant object should be 60 per meter. When you're looking at something far away, when your eye is most relaxed and at its thinnest, it should be 60 per meter. That should be its power. A person with defective vision, so they can't really focus very well on distant objects, they're a bit of a blur, their minimum power is 64 per meter. They actually can't make their lens thin enough. In other words, they bend the light too much and the image is formed before the retina. So we've got to calculate the focal length of the lens required to correct this defect. So as we said, the power of a normal eye when looking at a distant object P should be 60 per meter. This person with defective vision, their minimum power is 64 per meter. They can't make their lens any smaller than that. So everything will be a bit of a blur. So I want to find the focal length of the lens required to cure this defect. Well, the first thing to do is write down your formula for power. Power is equal to P1 plus P2. The power that you want is 60. The power that you have, we call this P1, is 64. And therefore, I want another power to be added to that, so I obtain getting 60. The power of my glasses or my spectacles. So I want to find out what is power 2. Power 2 is the power of my glasses. So you can see there very simply, power 2 is equal to 60 minus 64, which is equal to minus 4 per meter. The minus indicates that I'm going to end up getting a diverging or a concave lens. Now I want to find out what is the focal length of a lens with that power. So the lens that I'm going to be using in my glasses has a power of minus 4 per meter. My other formula that I'm going to write down is power is equal to 1 over F. So both those formulae are in your table book. You know where they are from your notes. So I'm looking for F. If you want, you can call these 2's. Doesn't matter if you do or don't. Slide the F2 up and the P2 down. So F2 is equal to 1 over minus 4 per meter. Throw the minus out in front. 1 over 4 per meter. I don't normally put the units in, but I will here just to make a point. So I end up getting minus a quarter. Put that into your calculator, do it in your head. That's minus 0.25. And bring the meter up, and that becomes, bring the nth power minus 1 up, and that becomes meters. There's minus 0.25 meters, which is fine as your answer. But if you want to turn it into centimeters, which we often do when we deal with lenses, that would be minus 25 centimeters. So either answer will do in that case. So for that question, 12 marks altogether. You're getting a load of marks anyway, aren't you, just for writing down the formulae that you're copying from your table book. And the last part of this question says, what type of lens is used? You might have guessed already, from P being negative, that's going to be a diverging or a concave lens. And name the defect that is happening here. So, the type of lens is going to be diverging or concave. 3 marks for that. And what is your defect? Well, I can't see distant objects very well, which means I can see close objects very well. So what do I do well? I can see close or near objects well. So my defect is called short-sightedness. So 3 marks for saying that. Okay, so you've got about 20 minutes to do that question. Even on the board here, we got it done quite quickly, well under the 20 minutes.